In the previous video, we introduced the concepts of dimensional analysis, and in this video we're going to continue with that by looking at one of the applications of dimensional analysis. And one of the situations where dimensional analysis can be used, or where dimensional analysis applies, is when we inspect homogeneous equations. Now, although that might sound quite complicated, all it really means is that the dimensions on the left-hand side of an equation must equal the dimensions on the right-hand side of an equation. If the dimensions of an equation don't balance and it isn't homogeneous, then the equation must be expressed in the wrong form. All equations must be homogeneous with respect to their dimensions. So let's look at a couple of examples. Let's start by looking at equations involving power. Now there's a couple of different power equations that we can look at. We have power equals force times velocity, and we also have power equals work per unit time. So what we could actually have, if we were looking at energy balances and power balances, is we could have an equation that stated that Fv equals W over T, or force times velocity equals work per unit time, or rate of change of energy. Now I've just created that equation, but what I need to check is that that equation is homogeneous with respect to its dimensions. So I'm going to inspect the left-hand side first of all, and when I inspect the left-hand side, I'm inspecting the dimensions, remember the square brackets, of force times velocity. Now, I'm not going to go through the process of deriving the dimensions for each of these again, because I showed you how to do that in the previous video. But what we do know is that the dimensions of force is ml t to the minus 2, and that's derived from mass times acceleration. And we know that the dimensions of velocity is lt to the minus 1. If you find it easier, we can say that that L is L to the power 1, and the second L is also L to the power 1, like so. Now, our dimensions are m. We only have one instance of m there. But what we have is we have two instances of L. We've got L to the 1 times L to the 1. And what we need to do, therefore, is add those two indices together. So L squared. And we have two instances of time. We have t to the minus 2 and t to the minus 1. Well, minus 2 plus minus 1 is minus 3. So t to the minus 3. So the dimensions of the left-hand side of our equation are ml squared t to the minus 3, or if you prefer, m to the 1 l squared t to the minus 3. Now let's inspect our right-hand side. And the right-hand side of our equation is work per unit time. Well, before I can do anything, I need to think about what we mean by work. And when we think about work, we think about a force being applied across a given distance, or force times distance. So the dimensions of work then are the dimensions of force times the dimensions of distance. The dimensions of force is ml t to the minus 2. And then we have the dimensions of distance. Well, distance is the same as a length. So would a diameter be. All of these things represent a length. So although I've written distance there, what I'm actually referring to is a length. So now I have ml to the 1, t to the minus 2, l to the 1, and I can combine those two l's together. I'll get m l squared t to the minus 2. But I'm not quite finished, because what I haven't yet worked out is the dimensions of work per unit time. Work over time, or work divided by time, all means the same thing. And the dimensions of work are ml squared t to the minus 2. And the dimensions of time is just t, or t to the 1 if you prefer. So now I have m l squared t to the minus 2 over t to the 1. Well, once again, using laws of indices, I need to subtract the 1 from the minus 2, giving me t to the minus 3. Another way of thinking of what we've just done there, in the top right-hand corner, I had t to the minus 2 divided by t to the 1. I can bring the t to the 1 to the top, but it becomes t to the minus 1. T to the minus 2, t to the minus 1. And now, because we're multiplying those two together, we're adding the indices. to give us the t to the minus 3. Now the whole point of doing this is to show that the left-hand side and the right-hand side have the same dimensions. So the left-hand side of our equation then has dimensions ml squared t to the minus 3. And when we compare that to the right-hand side of our equation, we notice that the right-hand side of the equation also has the dimensions ml squared t to the minus 3. Therefore, the equation is homogeneous with respect to its dimensions. Let's take a look at another equation, and this equation states that frequency equals 1 over 2 pi times the square root of mgl divided by I. Now this looks like a pretty nasty equation, but I wanted to pick something here that was a little more involved just to get some of these ideas across. Now the first thing that we know is that frequency, or our left hand side, is 1 over the periodic time. So frequency is 1 over periodic time. Therefore the dimensions of our left hand side are relatively straightforward. We have 1 over t to the 1, or just t to the minus 1. We can think about this idea of bringing the dimensions to the top. So our left hand side, the dimensions are just t to the minus 1. So in actual fact we're looking for some quite simple dimensions also for our right hand side. But the right hand side is more involved. Now the right hand side has a constant. So what we can do in actual fact is disregard that constant, and 1 over 2 pi is just a constant. It's 1 over roughly 6. So all we're left with is the dimensions of square root mgl over I. Now before we go too far, the dimensions of mass is relatively straightforward. The dimensions of gravity, well, gravity, or g, is acceleration due to freefall. So in actual fact, g is equivalent to an acceleration. One of the questions that this often raises is that students will ask, but I thought gravity was a constant. I thought gravity was always 9.81. And whilst that's true, gravity is always 9.81 on this planet. It's 9.81 meters per second squared. It's still an acceleration. It has a constant value, but it's still an acceleration. So if we return to the right-hand side of our equation, we've got a mass times an acceleration times a length divided by I. Well, I, and we'll inspect this, I is inertia. And inertia is best represented by the equation mr squared, mass times radius squared. You'll see different variants of this inertia equation depending on the object, but the dimensions are always going to be the same. So you might see an inertia equation, a half mr squared. Well, we've already said that constants don't affect dimensions. Or you might see inertia equations for different objects, such as a third ml squared. But the important thing is that the dimensions are always going to be the same. Mass times a radius squared. Now, a radius is just a length. It's the distance from the centre of a circle to the outside edge. So inertia has the dimensions ml squared. So before we concern ourselves with the square root here, let's look at the dimensions of mgl over I. So the dimensions of mass times acceleration, I'm just going to abbreviate that to ACC, times length. And we're going to divide all of that by inertia. Okay, so the top of our equation is mass. Acceleration is Lt to the minus 2. We've seen that before. And then we've got a length. And we're dividing all of that by inertia. And inertia, we've already said, is ml squared. Now the next step is to simplify what we have there. Now the easiest way to do this is to separate the top and bottom of our equation. So on the top, we've got an L to the 1 and an L to the 1. And we've got an m and a t to the minus 2. So we have m, L to the 1 times L to the 1 is L squared, t to the minus 2. And we're dividing that by inertia of ml squared. Now what we can do at this stage is we can cancel out some of these variables because we have an m to the 1 divided by m to the 1. Well, if we was to use our law of indices, the powers there would be 1 minus 1, giving us m to the 0. But we can do this in a more traditional way, and if we've got an m on the top of an equation and an m on the bottom, we can just cancel those out. However, it would always work with the law of indices. On the top we have an L squared, on the bottom we have an L squared. So our only remaining dimensions here is t to the minus 2. Now what we haven't done yet is we haven't square rooted our right hand side. So in terms of completing the analysis on our right hand side there, we need to square root t to the minus 2. And I'm just going to write this underneath. What we have is we have t to the minus 2 square rooted. Well, square rooting something is the same as doing a power to the half. Cube rooting is a power to a third, and so on. Now this time, because we're raising t to the minus 2 to the power half, we need to multiply those two numbers together. Minus 2 times a half is minus 1, giving us t to the minus 1. Now finally, what we can do is check. Our right hand side is t to the minus 1. Our left hand side is t to the minus 1. Therefore, the equation that we started with there is homogeneous with respect to its dimensions.